W will have the same value. However, delta P, that is pressure drop, may change depending on the inclination, because delta P star composed of the static pressure as well as the gravity head or the elevation head. So due to that, the component of pressure will be there. So accordingly, there will be a trade-off between delta P and this rho g delta H, you can say. So that is why you need to calculate the pressure drop for all the cases, and that actually gets changed, I think. If you look into the answers, this 58.28 kilopascal, then 682.832 kilopascal, and then negative pressure drop. This indicates the trade-off between the inclination and the pressure drop. But the summation of these two will remain constant, that is our delta P star. বুঝতে পারলাম এটা?
হ্যাঁ স্যার, স্যার আমি আগের দিনে বলছিলাম সেটা যে সেম থাকবে, তখন স্যার আপনি বলেছিলেন যে চেঞ্জ হবে, সেটা বলছিলেন।
আমি ভুল বলতেই তো পারি, সবসময় কোথায় লেখা আছে।
তারপরে স্যার দেবজিতে বলছিলাম, আমরা ডিসকাস করেছিলাম তো ওটা নিয়ে।
হ্যাঁ, না দেবজিৎ আমাকে তারপরে এটা হোয়াটসঅ্যাপও করেছিল। আমি অ্যাকচুয়ালি প্রবলেমটা ফ্র্যাঙ্কলি দেখিনি ভালো করে, তোমরা বলাতে আমি দেখলাম যে হ্যাঁ এটা ঠিকই পয়েন্ট আউট করেছো, তার জন্য ডিসকাশন লাগে। তো আমি অ্যাকচুয়ালি যেটা হাইলাইট করেছিলাম সেই পার্টটা আই থিঙ্ক আমি এখন তুলে দেওয়া উচিত, কারণ ওটা ঠিকই আছে, তাই তো? তোমরা এগ্রি করছো, তাই তো?
স্যার ওই 13 নম্বরের লাস্টের যে অঙ্কটা ছিল ওটাতে না মনে হচ্ছে ওই আপনার ফ্লো রেটটা আর কি অন্য এক্সপ্রেশন হবে বলে মনে হচ্ছে, কারণ কি মানে আপনি যে এক্সপ্রেশনটা দিচ্ছেন মানে ওই 1/12 সি কিউব বাই সি কিউব ইন্টু ডিপিডিএক্স, ওইটা যেটা ওটা তো প্যারালাল ফ্লো এর জন্য ভ্যালিড, কিন্তু এইখানে তো ফ্লোটা অনেকটা রেডিয়াল টাইপের হচ্ছে। তো মানে ওই ফ্লো রেটটা চেঞ্জ হলে আমার ওটা ক্যালকুলেট করে ইকুয়েশনটা মানে নিচে 6 আসছে আর কি, মানে ওই যে মানে বাকি সব মানে কি বলবো এইচ আর আপনার ওই প্রেসারের যে এক্সপ্রেশন বাকি সব সেম আছে, কিন্তু ওই যে মানে মেন যে ওই মানে রেশনাল টার্মটা আছে ওটা ওখানে 3/2 আছে, ওটা আমার 1/6 আসছে। এমনি আপনি যেভাবে বলেছেন ওভাবে করে, তো আমার মনে হচ্ছে ওইটা মনে হয় চেঞ্জ করতে হবে, কিন্তু ওটা চেঞ্জ করতে গিয়ে ওটার যে মানে ইকুয়েশনটা আসছে ওইটা কিভাবে সলভ করতে হয় সেটা জানি না আর কি, মানে প্রেসার আর আপনার ফ্লোয়ের যে ওই নর্মাল ইকুয়েশনটা আর কি আমি বলছি।
তাহলে এই জায়গাটাতে আমরা প্রাথমিকভাবে যেটা আমরা আগের দিন ডিসকাস করছিলাম, এটা একটা কারেকশন নোট ডাউন করে নাও। সো দিস শুড বি অ্যাজ ইট ইজ। আমি মুছে দিলাম হাইলাইটটা। So all shear stress will be same for all the three cases, right?
হ্যাঁ স্যার,
এটা তাহলে সেটেলড হলো। নেক্সট হচ্ছে 13 নম্বর। আচ্ছা, 13 নম্বরটা কিন্তু আমি যে প্রসেসটা বলেছিলাম সেই প্রসেসে করলে এটাই আসা উচিত, কারণ এইটার অ্যান্সার ভুল হওয়াটা খুব আনলাইকলি। আমাকে করে দেখতে হবে। এটা আমি প্রসেসটা করেছি, কিন্তু পুরোটা করে সেক্ষেত্রে আমাকে দেখতে হবে। বাকিদের কি মত? এটা কি এই যে এক্সপ্রেশনটা সেটা এসছে না আসেনি, মিলেছে না মেলেনি? প্রবলেম নম্বর 13 বাকিরা করে কি চেক করেছো?
না স্যার, আর মানে ওইটা আর দেখা হয়নি। বাউন্ডারি লেয়ারটা নিয়ে একটু ব্যস্ত হয়ে গেছিলাম, আর এটা মানে মনে ছিল।
আচ্ছা, হ্যাঁ বাউন্ডারি লেয়ার নিয়ে ব্যস্ত এখন তো ঠিক আছে। বাউন্ডারি লেয়ার ইভেন তোমার potential flow we have also circulated, so potential flow problems mainly we need to discuss, we need to have another day.
হ্যাঁ স্যার, ওইটা ডিসকাস কবে করবেন স্যার? মানে ওটা কি পুজোর পরে হবে নাকি
পুজোর আগে আর কি করে হবে, পুজোর পরেই করতে হবে।
ওকে স্যার।
Before puja, actually, this is going to be the last. I mean, officially, this is going to be the last class because tomorrow is a holiday, and next week it will be puja.
স্যার তাহলে আপনি ওই বাউন্ডারি লেয়ারের
ওই প্রবলেম শিটটার মোটামুটি ইয়েগুলো ঠিকই আছে, মোটামুটি উত্তরগুলো মোটামুটি মিলছে।
Second step, বলো।
আপনি তাহলে
একটা কোয়েশ্চেন একটু ভুল।
অরণ্যর কিছু একটা বলছিলেন।
হ্যাঁ স্যার, আমি বলছি যে আপনি তাহলে মানে যেহেতু পুজোর তো অনেকদিন ভেকেশন আছে, 22 তারিখে সম্ভবত খুলবে, তো যাই হোক আপনি ওই বাউন্ডারি লেয়ারের প্রবলেমটা একেবারে দিয়ে দেবেন, তাহলে এই পুজোর মানে ছুটিটার মধ্যে ওটা কমপ্লিট করে নিতে পারবেন।
প্রবলেম সেশন বাউন্ডারি লেয়ার, ওকে ওকে, হ্যাঁ ঠিক আছে, সেটা দিয়ে দেওয়া যাবে। বাট আই থিঙ্ক আমরা পুজোর পরে বেসিক্যালি 25th probably university will open, I mean online or offline, whatever. So we will remain in online as of now because of no notification from government. So whatever it is, so ওই সময়টা actually 25th onwards, before Kali Puja, because during Kali Puja also we will be having some few days holiday. So in between you can expect to have one test, okay? সেটা class test form এ হতে পারে or some kind of a practice test in MCQ format, something like that, assignment format. That so you should remain mentally prepared for that, because as I said in the earlier class also that boundary layer today, whatever discussion we will have, up to that maybe we can have the content of or the syllabus of that particular test, okay? So that announcement, formal announcement we will have. I mean, let me have a discussion with Professor Manna. And but we are having a plan to conduct a test during that period, either in form of a formal class test or internal for 30 marks, because I think I don't know whether you are aware of this particular news that this semester also there will be, I think, one internal only. Okay, 30 marks. So as of now, it is in online. It will be in online mode. But if it, I mean, if the university gets open in physical form, or and if some government notification come, then this online form, this online mode of exam may also get changed. Okay, so that uncertainty is there, but so keeping that in mind, either we can have a practice test or a formal test, whatever. So we will let you know. Okay, but regarding, yeah, we can circulate the problem sheet on this boundary layer flow. Okay, so that we can circulate as you are requesting, no problem. So I mean, those who want to start doing that, start trying to solve these problems by going through the video lectures, because all video lectures are there, I think, already with you, all the topics boundary layer. Some 7-8, I think, like that. Lecture videos are there. ঠিক আছে, তো সেটা করে দেওয়া যাবে, অসুবিধা নেই। Okay, so regarding problem 13, I have to do it by myself, so that if it is coming correct or not, I have to cross check, and also I am requesting others to cross check as well. Okay, so that this answer it's very unlikely to be wrong anyway, but it may happen. So we have to check. Okay, so with that, I think viscous incompressible flow, problems on viscous incompressible flow, that discussion we can end. All right. So next discussion will be on problems on your potential flow. So I hope you have already started working on that. So after puja, probably we can have a class. In between this vacation, I don't think all of you will be agreed to have a special class because we have lost some meat due to natural situation, unavoidable situation. So we can have a compensatory class, uh, maybe within this vacation or after vacation. Okay. So that you can also through here we can have the date. If possible within vacation, one class can be taken. So have you gone through this boundary layer flow?
Yes, sir.
Yeah. So
ফার্স্ট ভিডিওটা দেখেছি।
first video I think is the introductory video. So actually this boundary layer flow, as you can see on your screen, the very introductory part. I mean, and it is the date, the period actually from when this particular boundary layer study of boundary layer came into picture. Is quite we can say new, just some 100 years more, just a little bit of 100 years old. So it is 1904 is the period when this concept of boundary layer was pointed out by Ludwig Prandtl, and he is the pioneer, father of this concept of boundary layer flow. That actually opened a new, or you can say that actually answered so many unsolved situations, and also gave engineers a way to design a more efficient this bodies which move through fluid, air or water whatsoever. So this boundary layer is basically, I mean, although it is a layer defined like that, but it is there is no such demarcation between in a flow field between the boundary, the area or the volume of fluid within which you are having this prominence of the boundary layer effect, or if the effect of boundary layer is significant, you can say, and the zone where the effect of boundary layer is not that significant, as it is, I mean, the postulate of this Prandtl says we can have two distinct region of or regime of flow, and classify it in two parts, one of which already we have gone through, that is the inviscid or potential flow, which is beyond the boundary layer, where these velocity gradients are small and effects of viscosity may be negligible. And the other regime is the flow within which the shear stresses are of prime importance. So that is the most keyword you can say. The shear stresses are of prime importance. Is that the region which we can denote as boundary layer? And this entire study or this entire discussion is based on the very basic assumption or the fundamental characteristics of flow, that is continuum. I mean, it also satisfies the continuum concept. That means even you remain within the boundary layer, it doesn't mean that you are violating continuum concept or the no slip and the no slip condition. That means which means the velocity of fluid related to the surface is zero. So these two fundamental characteristics are being satisfied within the boundary layer as well. So let me just ask you, if those who have gone through the very introductory part, we had a viscous incompressible flow topic just like some time back. We are discussing the problems on it, where actually we considered the effect of viscosity. And in the boundary layer flow, as you just now we have seen that it is also the flow regime where we need to incorporate, we need to consider the effect of viscosity of the shear stress. I mean, basically due to shear stress, we have the viscous effect. So what is the difference? Why, or in other words, why it is relevant to study boundary layer flow? And as already we have studied viscous incompressible flow, what is the difference? Anybody?
স্যার বাউন্ডারি লেয়ার ফ্লো এর মধ্যেই কেবলমাত্র ভিসকাস এফেক্টটাকে আমরা কনসিডার করবো, তাহলে ওখানেই আমরা এই ভিসকাস ইনকমপ্রেসিবল ফ্লো এর কনসেপ্টটা লাগাবো। আর বাইরে স্যার যেহেতু মানে ওখানে ভিসকোসিটির এফেক্টটা খুবই নেগলিজেবল, 0.99% অফ পিচিং ভেলোসিটি, তাই স্যার ওখানে আমাদের মানে পোটেনশিয়াল ফ্লো এর কনসেপ্ট লাগালেই চলবে, যাতে ইকুয়েশন গুলো অনেক মানে
no, that's fine. My question, I think, is little different thing actually I am asking. My point is that we have studied viscous incompressible flow. What is the difference between incompressible flow and boundary layer flow? To be more direct, perhaps. That is my question. We have already studied the viscous incompressible flow, where we had the viscous
incompressible flow তো পুরোটাই মানে ফুললি ডেভেলপড এর উপরেই ধরা হয়, কিন্তু বাউন্ডারি লেয়ারটা তো পুরোটাই মানে পুরো ফ্লো রেজিমটা দিয়ে আমি কাজ করতে পারবো আর কি। মানে একটা পাইপের মধ্যে দিয়ে আমার ফ্লো হচ্ছে, আমি ওই ভিসকাস ইনকমপ্রেসিবল ফ্লো নাভিয়ার-স্টোকসের ওই হ্যাগেন পজিটিভ লাগাতে পারবো খালি ফুললি ডেভেলপ হওয়ার পরেই। কিন্তু আমি এই বাউন্ডারি লেয়ার থিওরিটা জানলে আমি ধরুন খুব কম লেন্থের একটা জায়গায় কিছু একটা মানে ইঞ্জিনিয়ারিং কিছু একটা করতে চাই, তবে সেইটার পজিশনটা জানতে পারবো, বা সেটা সেখানে কি রকম প্রেসার ডিস্ট্রিবিউশন ভেলোসিটি ডিস্ট্রিবিউশন হচ্ছে সেটা আমি জানতে পারবো, সেটাকে ইউজ করতে পারবো।
Actually, yes, you have pointed that right way, because and that actually in this figure the answer also is evident here, the difference between viscous incompressible flow and the boundary layer flow. This particular schematic diagram where we are having a free stream flow of the passing over a plate. Okay, so the place where we are having a velocity uniform that is denoted by U naught, and when it approaches immediately what happens at the boundary, I mean keeping in mind the two basic, one of them is no slip condition. So basically at the leading edge, immediately when the velocity or the flow field actually is being passing over to that leading edge, the velocity of the particles adjacent to that particular plate will be retarded, and it will attain the velocity of the plate itself. And if we consider the plate to be stationary, then this U naught will remain not as U naught, rather it will become zero because of this no slip condition. So that indicates there will be retardation, and because of that, I mean, this figure, you can see it started with this thing. From this point here, we are having zero velocity point, right? But as this free stream passes over the plate, that means when it enters a certain length of the plate, gradually this effect of retardation changes. Means at the beginning here the velocity is 0, but immediately after this point on y direction, you can expect to have more or less this velocity u0. Okay, but as you go in this x direction inside, more and more layer of fluid in the direction of flow gets affected by this retardation, and due to that we can have a velocity profile something like this. That means affected layer of the fluid where we are having no longer the velocity in the direction of flow to remain u0, rather it starts from 0 and then it actually increases, and after a certain distance in the direction of y, it approaches the free stream velocity. And distance at which you are having the velocity more or less very close to the free stream velocity is having a very significant role in the study of boundary layer, which we call as the boundary layer thickness, which is highlighted on your screen in this text. And also it is being shown in the figure. So basically I am talking about this distance. So theoretically, when the velocity in the direction of this fluid, basically the component of velocity u we are only treating. If you are having two-dimensional velocity distributed flow domain, or if it is three-dimensional, then in all the other direction, the same type of variation one can expect. Okay, so here it is basically a free stream of velocity u0, which is coming in contact with the plate to understand the growth of this boundary layer. So as I have said that as more and more amount of fluid volume is getting affected with this shear stress and the presence of the solid boundary, so this velocity profile is gradually getting this kind of shape. And after a certain length, one can expect to have a more or less uniform velocity profile. So that particular, after a certain means this L I am talking about. So after a certain length, if you have this velocity profile remaining uniform, so basically in the direction of x, this profile is not changing. That is what we called as fully developed flow. So that is one particular domain we are talking about. Okay, but within which also there is the effect of boundary layer, because basically the effect of boundary layer means you are considering the viscosity effect. Okay, so that particular region where you are having a fully developed flow, but the effect of viscosity is being considered, is the one which we have already studied. That is basically the viscous incompressible flow, considering the flow to be constant density, right? But boundary layer flow encompasses the formation of this boundary layer, or you can say the formation and its growth to attain the developed region. Okay, so that is why this is basically, you can say, the growth of the. Okay, so or in other words, this is basically the imaginary line demarcating the two distinct flow regime. So by the definition of this boundary layer thickness, which is basically that length or in the direction normal to the flow, where the velocity is theoretically equal to u naught. Okay, but that is kind of an asymptotic approach. So so delta x at infinity will be at will give us the velocity u as equal to u naught. Right, because theoretically it will be like that. However, or in other words, here also we can say that the effect of viscosity will be there in the normal direction up till infinity, because no fluid is invisible. Okay, so actually the potential flow which we recently studied, where we considered the flow to be invisible, so that is an assumption. But that assumption is reasonable, as here the way we define the boundary layer thickness is when the velocity u parallel to the plate reaches 99%. So this is not the 100%, 99% of the external velocity or the free stream velocity u naught. Okay. The last 1% actually it will be reached at delta x infinity. So, but the 99% will be reached at a very small dimension of delta, which is much lesser than the characteristic length L. This L is actually noted as the characteristic length, and this is basically kind of an exaggeration in this figure. You can see the delta x, which is shown to be comparable with x, but in actual case, this delta x is much lesser than L. I mean, L is when you can expect to have 99% of the external velocity, u naught. Okay, so that is the departure, you can say, pure mathematical concept to the more practical one, because otherwise you need this mathematically delta x at infinity will give us the velocity equal to the external velocity. Okay, so then actually we define the boundary layer, the description, a more elaborate description we had, and that is basically being adopted from the textbook Massey. So, where like the kind of flow you have studied, or the characteristics of flow which composed of laminar turbulent transition, in case of a flow over a flat plate also, within the boundary layer, one can expect to have this during the formative stage, at the or near to the leading edge of the plate, we can have nature of flow which is very orderly and disciplined manner, with that is basically laminar flow can be expected. And with the growth of boundary layer, this laminar region cannot able to hold because of larger momentum. So it actually starts breaking, and that's so that means breaking means this motion in a straight line manner is not being sustained. So that region is basically known as the transition, and after that further distance away from the leading edge or in the direction of x, we can say, what happens actually, the mixing is getting more and more, and that region is known as the turbulent region. Okay, so within the turbulent region also, we can have a very thin layer where it is some kind of a laminar boundary layer kind of situation, but the thickness is more nominal, which is called as the viscous sublayer. It is shown here. Okay. So this is a typical representation of growth of boundary or description of the boundary layer. Okay. So in our study, actually, we have started with a flat plate parallel to the direction of the flow, and we considered that there is no other solid surface nearby, and the pressure of the fluid is uniform. So the second consideration is important in a sense. If you are, instead of one single flat plate, if you consider a flow between two parallel plates, that is what we did in case of viscous incompressible flow. So in that case, if two plates are being separated by a very small distance, so that means if you are having a flow through these two plates, I mean, you have to consider the effect of boundary for both the plates, the effect of the two boundaries actually. So there will be a composite effect. Okay. So as a starting point, that is basically being avoided. Okay. So it is only a single plate over which flow is occurring. This is a consideration. If one can understand that properly, he or she can able to analyze the case where you may have another boundary or rigid surface nearby. Okay. So that is the reason of this consideration. And the third one is again some kind of a simplification to assume that the pressure of the fluid is uniform. Okay. And actually we moved on to find out the governing equation for 2D laminar boundary layer. So here a new kind of treatment we have made, and that is what is called basically order of magnitude analysis. So here it is being written. So first of all, we are considering the flow to be steady, incompressible. So this is already, again, I mean, it is the same kind of a consideration what we did in viscous incompressible flow as well as in potential flow. The same remains valid here as well, steady and incompressible flow. So the moment you consider it, your continuity equation gets this form, along with the two momentum equation of the Navier-Stokes equation and scalar form for x and y direction or the two component. The consideration here is 2D flow. So you can have U, you can have V. U and V are the two component of velocity that may exist. And there could be the gradients in the respective direction. And pressure also, we can have del P del X and del P del Y. And along with it, the component of viscous force. So that is basically the second term of your right hand side of the equation. We are talking about this term. Okay, so this is the general representation. This 1 and 2A, 2B are the general representation of your the two governing equation. One is the mass balance or mass conservation, and the other is the momentum equation. Okay, so then, I mean, so that is the beginning of the story. But then actually we have tried to use a particular method or analysis technique. The basis of the technique is very simple. I mean, basically, you know, if I tell you, I mean, have you understood this order of magnitude analysis? Anybody have gone through this?
Yes, sir.
Sir.
So have you understood this?
Yes, sir.
Sir, not fully, sir.
Okay.
No, sir, বুঝতে পারছি না, sir.
Okay. I mean, typically,
মানে এটা বুঝতে পারছি যে ওর অর্ডারটা বেশি হয়ে যাচ্ছে, ওটা কম হয়ে যাচ্ছে, তাই ওর রেসপেক্টে নেগলেক্ট করতে পারছি, কিন্তু মানে অর্ডার মানে ঠিকঠাক বুঝতে পারিনি মানে হচ্ছে ডিটেলস।
yeah, I mean, here I mean, this problem normally students face. I mean, to appreciate this approach. I mean, this is a valid approach, because basically, typically, say, for example, this we can write, I think, isn't it? 1000 plus 0.01 can be reasonably written as equals to 1000, isn't it?
Yes, sir.
স্যার অর্ডার অফ মানে অর্ডার অফ কোনো ভেরিয়েবল মানে কি স্যার? মানে মানে ওই ভেরিয়েবলের মানে পাওয়ারটা বলতে চাইছে না মানে কি বলতে চাইছে স্যার? ওটা
অর্ডার অফ ম্যাগনিটিউড মানে যেটা আমি লিখলাম সেটাই। হোয়াট ইজ সে দিস ইজ ইয়োর এক্স and this is your y. Okay, so order of magnitude of x is in the level of 1000, or it may be 2000, it may be 1500, it may be 5200, but its magnitude is in the order of 10 to the power 3, whereas the magnitude of y is in the order of 10 to the power minus 2. It could be minus, I mean, it could be 0.05 or 0.058, 0.02, something like that. Okay, so that is why, I mean, instead of writing the exact numerical value, we can write that the order of x will be like this, and order of y is in the order of 10 to the minus 2. Means something from 10 to the minus 2 to 10 to the minus 1. এই রেঞ্জে হয়তো ওটা ভ্যারি করে, বুঝতে পারলো? তো this is some by some logic, by some rationale. If we can establish that this can be the situation where order of x is much higher than order of y, so that in a particular equation like this, whatever we have written, we can write, instead of x plus y is equal to 1000, you can write x equals to 1000, as because order of y is much less than order of x. So this is the reasoning. Okay, depending on that, we can drop a term in an equation, so that the treatment of the equation can be done in an analytical manner. Otherwise, you may require to go for a more complicated method to solve a particular equation, and after that, you may come to the solution, which with this order of magnitude analysis method, I mean, whatever truncated form of equation you have derived, the solution using that particular equation may be very close to the one if you could have solved it for a full-scale Navier-Stokes equation. Okay, so that saves lots of effort actually, and here the starting point you may have already observed while describing this boundary layer thickness. One thing is highlighted, that is this one. The delta is much less than L. That means here delta as a variable, because delta as a variable means if we are going for understanding the growth of this boundary layer, then definitely delta is a variable, and it actually varies in the direction of, I mean, x. So that is why delta is a function of x. So I mean, in the direction of the flow, actually, if we treat it, if we want to know the characteristics of this delta. So this variable delta is having order of magnitude, we can say from 0 to some value which will be much, much less than this L. L could be 1 meter, 2 meter, 100 meters, something like that. You can have a plate of 10 meter length, you can have a plate of 100 meter length also. Okay, but the formation of boundary layer and thereby attaining the fully developed region, because once you have the fully developed zone, then it is, I mean, implicit within the definition of fully developed flow that point onwards, your delta won't change, isn't it? Because the velocity profile will remain same. So that means that this will remain in the direction of flow. So this distance will remain same. So that is actually my delta. So delta x is varying from 0 to delta. And here delta is much, much less than L. So that we can say that order of this delta is much, much less than the order of the characteristic length L. Okay. Is it understood? Do you agree with that? Because it is really this length, this boundary layer, this thickness is very, very less in comparison to this dimension L. The logic, if you are having any problem still now, you can ask me. You can ask for further clarification, or else we can go for the we can go through a quick.
এখানে তো স্যার অ্যাম্বিগুইটি আসতে পারে, মানে ধরুন মানে একটা যেটা ধরুন 10 to the power -2 এর আছে, ওটা ধরুন খুবই ছোট ভ্যালু নিয়েছি আমি, এবারে 10 to the power -3 এর কাছাকাছি চলে গেছে, এত ছোট ভ্যালু মানে এক আর কি, ধরুন জাস্ট নর্মাল 10 to the power -2 ওটা একটা ভ্যালু, আর একটা ভ্যালু ধরুন মানে 99 into 10 to the power 3 বা ওরকম টাইপের কিছু। তো সেক্ষেত্রে তো মানে একটা তো একটা আর কি ক্লোজ টু 10 to the power 4 এ চলে গেছে, বাট ওটার অর্ডারটা তখন 10 to the power 3 আছে, কিন্তু আরেকটা মানে খুবই ছোট, তো মানে ভ্যালুটা তো বিরাট রেঞ্জে ভ্যারি করা যাওয়ার কথা না সেই অনুযায়ী। মানে বলতে চাইছি যে মানে এই অর্ডারের যে ব্যাপারটা, এই অর্ডারটাও তো মানে আমি যখন একটা পার্টিকুলার অর্ডার ফিক্স করে দিচ্ছি, তারপরেও তো একটা বিরাট রিজিয়ন পাচ্ছি ওটার ভ্যালুটাকে চয়েস করার জন্য। মানে ইনফ্যাক্ট অর্ডারটা যখন বাড়তে বাড়তে যাবে, আমার তখন মানে কি বলবো, আমার র্যান্ডমনেসটা বাড়তে বাড়তে চলে যাবে ওটার সঙ্গে সঙ্গে করে ভ্যালুটা এক্সাক্ট ভ্যালুটা পৌঁছানো। তো সেটাতে খুব
basically here the comparison is, here the logic is, if say your order of x, I mean if your order of x is decreasing and order of y is increasing, so that at some point of time these two orders of magnitude can be comparable. So instead of 1000 and 0.01, maybe your order of x gets decreased and it comes around say 100 or 10, and after getting increased, this order of y it may comes around 5 or even 1 maybe. When this situation arises, then definitely your consideration of this x is nearly equal to 1000 will remain violated, will become a violation. But if the situation is just the reverse, means if your order of x getting increased more and more, I mean we have started from 1000 or 10 to the power 3, and it is getting increased 10 to the power 4, 10 to the power 5, and your order of y remains fixed. It remains in the order of 10 to the power -2. Okay. I think you are trying to say of this case.
আমি বলতে চাইছি মানে সলিউশনের ব্যাপারটাকে বলতে চাইছিলাম, আমি হচ্ছে মেইনলি সলিউশনের ব্যাপারটা বলতে চাইছিলাম। মানে ধরুন ভি এর অর্ডারটা হচ্ছে 10 to the power 4, তাহলে ওর মানে ওর যে রেঞ্জটা আসছে ওটা তো বিরাট বড় আসছে, মানে অনেকগুলো সংখ্যা পাচ্ছে এই মাঝখানে 10⁻³ আর 10⁻⁴ এর মধ্যে। তো তো মানে অতগুলো সংখ্যার মধ্যে এক্সাক্ট ভ্যালুটা কোনটা সেটা পাওয়াটা ওটার ব্যাপারে বলতে চাইছিলাম আর কি। মানে
No, no, that is a different issue altogether. The solution part for the, I mean, x plus y is equal to 1000. If you want to solve this equation, you need two set of values, x1, y1 and x2, y2, isn't it?
yes,
Right? If you want to solve for x
Yes,
and
sir.
y, for where x plus y is equal to 1000, at least at two different points you need to know the numerical value, then you can solve it. Else, if it is x equal to 1000, you are having a solution in your hand. এখানে জেনারিক্যালি আমি এটাকে x plus y বলেছি, x could be del u del x, okay, and y could be del p del y, something like that, but these two summation should remain close to 1000. But if you are having your del u del x much greater than del p del y, so you can completely neglect about the change of p with respect to y, or in other words the gradient del p del y you can neglect. So you are having del u del x is equal to 1000, and if you find that u is only a function of x, so it becomes du dx. The moment it becomes du dx, then you are having a straightforward route to solve this equation du dx is equal to 1000 or some constant c. Forget about 1000, du dx is equal to c. If you are having a form of equation like that, so straight away you are having a equation u is equal to cx plus some constant, okay, with some boundary condition.
আচ্ছা বুঝতে পেরেছি ব্যাপারটা, বুঝতে পেরেছি স্যার।
Okay, so this is actually
Yes sir, yes sir, clear sir.
this is actually the, I mean, philosophy behind order of magnitude analysis. So by comparing the terms means not in exact, not in its full numerical value. The way I have given you or I have shown you is just the one example. It is basically the comparative, study, you can say, between two entity or more entity, and by understanding the behavior, by understanding their effect, with logic, of course, one can drop certain terms to get a more handy equation which can be solved in an analytical manner. That is the objective. Okay. So keeping that in mind, the first thing that we have started, as I say, is the dimension of or the magnitude of this boundary layer thickness in comparison with the characteristic length L. So here some notations are being written where u as order of u naught. U means this velocity u could vary from 0 to the free stream velocity u naught. So that means we actually attributed the order of u as order of u naught. All right. Then the order of x, that is our x direction, is attributed to order of this characteristic length L. And the order of y, that means in y direction you have the dimension of this boundary layer thickness delta. So the y dimension, in y direction, the magnitude will be at most the order of delta. So by this we are having a domain, a flow domain within bound. This is, one should not get confused about this order of magnitude analysis. Whatever we are doing here it is basically confined within the so-called boundary layer, demarcated by that particular line, which is, of course, conceptual. Okay, that is, I mean, whatever analysis we are doing, that is inside this line. This is our domain now. This domain already we have gone through, that is the potential flow. Okay, now we have moved inside this particular layer. So within this layer, so again I am referring back. So basically this layer, we are having the description in terms of the order of magnitude. One is U, then X, and then Y. So they are being defined by the respective known order of magnitude. What does it mean? I mean, the moment you are having a free stream means you should be aware of what is the magnitude of U naught. The moment you are having a plate, one should be, I think, it is expected that you should know the length or the order of the length L of the plate. That means the dimension of this plate should be expected to be known. And then the fully developed flow, where this particular delta, that is the boundary layer thickness, what is the maximum boundary layer thickness, where from the point onwards where the velocity profile is not going to change. So these are the three basic parameters by which the analysis has been started. And then if X is in the order of L, then del X will be in the order of 1 by L. That is obvious, I think, one can understand. So based on that, using the continuity, we have tried to evaluate the order of the other component of velocity, that is our V. Okay. So that means, I mean, in order to remain in this equation, del V del Y term, you need to have the order of magnitude of V like this. It should be the order of a composite factor, that is U naught, delta, and L. So V should be in that order so that you can have both the terms comparable. Okay. So as it is a 2D flow, we need to have both this velocity. I mean, okay. So by knowing the order of U, one can predict about the order of V for a steady incompressible flow, which needs to be satisfying the continuity equation. Is it clear? So that is the way by which one can find out what should be the order of the velocity component V. So once you know this velocity component V, its order, I mean, not the exact value, then you can proceed for the two components of Navier-Stokes equation in x direction. If you then evaluate the order of the individual term, particularly in the right in the left hand side first, it can be seen that these two terms, U del U del x and V del U del y, is having order of U naught square by L. Okay. So, I mean, like fundamental dimension, here actually we are having U naught, L, and delta as our three fundamental parameters. So, I mean, with respect to those three parameters, if you denote some order of a particular quantity, one can have the idea. So that is our main philosophy. I'm repeating 1 second. Okay, so order of this U del U del x and V del U del y will be U naught square over L. Okay. Then we came to analyzing the right hand side terms, and we picked up first this particular viscous terms, and in which other than this new, that is the kinematic viscosity, if you look into the other two terms, bracketed terms, del 2u del x2 giving us the order of u naught over L square, and whereas the second one, that is del 2u del y2, is resulting the order u naught over delta square, right? And we are having delta much lesser than L, so that simply if we compare these two terms, we can neglect this first one, that is del 2u del x2, because delta square will be more negligible than L square, isn't it? Means again, this 1000 and 0.01, and if you now compare 1000 square with 0.01 square, okay, and if it goes to the denominator, so basically the second one, if it goes to the denominator, that 0.01 square, something divided by 0.01 square, and that something is the same for the two quantities, isn't it? Here both numerator are same, u naught and u naught, but it is being divided respectively by L square and delta square. So I think this logic is quite understandable why after this comparison we are neglecting del 2u del x2 with respect to del 2u del y2. Is it clear?
Yes, sir.
Okay, so without incorporating this new, because this is a common multiplier, na? So just by comparing these two quantity, we can say that this should be the term del 2u del y2 that will remain in the competition. Okay, so simply if you just consider this, the most part of this bracketed term has been considered. But then actually to remain comparative, with the left hand side term, so the composite one, that is nu del 2u del y2 should be having the order of magnitude of this u naught square by L. Okay, so in the first step, after neglecting del 2u del x2, we have this form, and then you need to understand that whether you can keep this term, so minus 1 by rho del 2 del x. If you need to keep it, it should also have the order of magnitude u naught square over L, isn't it? Because otherwise, it won't be a meaningful term in the expression. So that is the basis. Okay. So this term should be having the order of this, and also this term should have this order. Okay. So from this analysis also, there is a corollary, you can say, which is being done next, where, as you can see in your screen now, that means this u naught square L should be of the order of nu u naught over delta square. Nu u naught delta square is basically our nu del 2u del y2, because u is in the order of u naught, and delta and y square is of the order of delta square. Okay, so this we can write. This is the comparison between the order of the left hand side terms and the term nu delta u, del u del y square. Okay. So then some manipulation actually reached to a situation where one can have another very important relation, that is the ratio of delta and x as a variable, or I mean delta and L, that is the characteristic length, okay, which is being expressed in terms of what is our very known parameter, that is the Reynolds number, which is being expressed as du naught L by nu, where L is the characteristic length. This is not, I mean, for a pipe, this definition of Reynolds number is for a flow over a flat plate. Okay, so the characteristic length is L, and if you think about the formation growth of the boundary layer, then this L can be replaced by X, where it is a variable X. So with X, you are having a different Reynolds number. So that actually led us this relation delta by X. It will be of the order of 1 over square root of Reynolds number at any X, denoted as Rex, Re suffix S, X. Okay. For flat plate, up to a Reynolds number 2 10 to the power 5, the boundary layer remains laminar. So one can here straight away see the difference between the Reynolds number that we normally gone through for a flow through pipes, and that for a flow through this flow over a flat plate. Okay, so in a similar manner, then if you deal with this y momentum, what we get is that then this entire y momentum can be neglected with respect to the x momentum, and also the pressure P, that is del P del y, the order of 1 by rho del P del y, is found to be u naught square delta over L square, which if you compare with the one for x momentum, that is our u naught square by L, that gives us this ratio del P del x and del P del y to be in the order of L by delta, which is much greater than 1. Or in other words, you can say that del P del x is much higher than 1. So the gradient of P in the direction x is very high. If at all you are having any gradient of pressure, sorry, it will always be much higher in the direction of x in comparison to y. I mean, in other way also it can be explained. See, as this delta is much smaller in dimension, if you consider the variation of pressure in y direction, I mean that small dimension, within that small dimension actually, the variation of pressure is always very small. And above the boundary layer, the variation is governed by this energy equation of the Bernoulli's equation. Okay. So because of this pressure variation negligible in y direction, we can have the same Bernoulli's equation variation in terms of pressure to be there inside the boundary layer. That we actually use that particular logic in the later part of the boundary layer theory. So For the timing, we obtain this del P del X is much greater than del P del Y, so that one can neglect del P del Y, and instead of writing del P del X, now you can write dP dx. Okay, and this entire order of magnitude, or that is this one, is much less than this one. So this entire equation 2b can be neglected as written here with respect to that of equation 2a. So with this logical step-by-step approach, one can lead to the final form of the boundary layer equation, or the governing equation of boundary layer, to be as written in equation in form of equation 3. That is del u del x plus del v del y equals to 0. That is the continuity equation, and modified x momentum equation, in which actually we drop the one viscous term only, keeping the other term. So that is in this fashion, and we do not have any y momentum equation. So the entire y momentum equation is going to drop, and del P del X is being replaced by dP dx. Okay. So before proceeding further, we had two very important definitions associated with this boundary layer thicknesses. So any questions up to this order of magnitude analysis?
No, sir.
Clear.
Yes, sir. Clear.
Okay. So regarding these two definitions, which are actually displacement thickness and momentum thickness, one actually comes from the mass flux related issues, and the second one is related to the loss due to momentum, the momentum loss associated with the existence of boundary layer. Of course, I mean, one can understand that because of the existence of the boundary layer, and thereby you are having a velocity profile not like the one for an uniform flow. It is actually a velocity which is a variable. That indicates if there is no boundary layer, you can have some amount of mass flux or momentum flux taking place through the particular region, which gets affected when there is a presence of boundary or a rigid boundary or a surface, okay, over which flow is occurring. Okay, that means because of the presence of a boundary, your flow gets affected. Okay, and how it is being affected, you actually you're going to lose some amount of mass flux due to the presence of this boundary. You may lose some amount of momentum flux due to the presence of that boundary. Okay, so that loss of mass flux or momentum flux can be represented or can be replaced as if by some equivalent length of shift of the boundary to compensate for the loss. Okay. So this is the way by which these two definitions evolved. One is the displacement thickness and the other is momentum thickness. So as it is written here, it is basically the first one that is denoted by delta star, is displacement thickness. It is the distance the plate would be moved so that the loss of mass flux is equivalent to the loss of boundary layer the loss the boundary layer causes. Okay, so if you look into the this figure particularly, I think you can understand. Okay, so this line, this line is this particular curve line is the velocity profile. Okay, so without the arrows actually. Okay, so because of this velocity profile, there will be some amount of mass flux loss. If instead of this velocity profile, if you are having a velocity profile like this, typically representing the free stream flow, isn't it? That means in case of free stream, we have this kind of a velocity profile. Okay. So this line actually is a profile indicating that one. Because of presence of the boundary, that is this one, this is the boundary over which the flow is now occurring, the profile gets changed, and then now it is like this. Okay. So what is the amount of loss? That is basically this area and this velocity u instead of u naught. This is going to be the loss of mass flux, isn't it? I mean, rho is not changing, so rho is just a factor here. So the difference of the two mass fluxes, one without boundary layer and the other is with boundary layer, can be expressed in this manner, which is being shown here. So mass flux per unit width, if you do not have any boundary, can be written like this: integration 0 to infinity rho u naught dy. And if you are having the presence of boundary layer, then the actual mass flux is basically instead of u naught, you need to write u only, so that the others are remaining same, rho and dy. So it will be rho u dy. The integration is 0 to infinity. Here actually the theoretical definition is, it has been started with the theoretical definition where up to infinity the boundary layer goes on developing and developing. Okay, so that is basically the amount of loss which is now being written in this manner. That is rho u naught minus dy. Typically this area actually is denoting that. Okay, so this is the loss. Now the equivalence. The equivalence is shown here. So instead of having the free stream flow over the entire boundary, as if you shift the boundary delta star distance above and considering the flow to be inviscid or a potential flow is occurring over the boundary, so that this amount of loss is there because of the shifting of the boundary. This is just a conceptual thing. Okay, we are not doing anything in reality. This is just an equivalence. Okay, so if you shift the boundary from 0, that means this is the actual location of the boundary. If it is being lifted up to a distant delta star, and then you consider the flow to be potential flow or inviscid flow, such that you can write rho u naught delta star. Okay, that is the mass flux per unit width, right? For which region? For this region, isn't it? And this is equal to the loss of mass flux due to the presence of boundary, which is this one just before we have obtained Okay, so if these two are equated, then you can have the knowledge of delta star in terms of u naught, and then basically it is being approximated in terms of the boundary layer thickness delta. That means the limit 0 to infinity is being changed to 0 to delta A. বোঝা গেল?
হ্যাঁ স্যার।
হ্যাঁ স্যার, কেন স্যার মানে বাউন্ডারি লেয়ার থাকলে স্যার ওখান থেকে মানে কম মাস ঢুকবে, তাই তো? মানে
Because of the retardation, na, you are having a change in the velocity. So if velocity gets changed, so your flux gets changed, na?
yes,
যদি ভেলোসিটিটা চেঞ্জ না হতো, যদি পুরোটাই ইউ নট হতো, তাহলে তো আমার মাস ফ্লাক্স তো কিছু চেঞ্জ হবে না। যতটা মাস যাওয়ার কথা ততটাই যাবে, কারণ মাসটা তো ক্যারিড হচ্ছে বাই দ্য ভেলোসিটি। So if velocity gets altered, instead of having u naught, you are having a variable velocity u, which ranges from 0 to u naught. সেটাই হচ্ছে বেসিক্যালি আমার মাস ফ্লাক্সের যে লসটা, সেটা আমার ওখান থেকে বেরিয়ে আসছে। এবারে এটা একটা ইকুইভ্যালেন্ট প্যারামিটার দিয়ে জাস্ট ডিনোট করা হচ্ছে টু denote the mass flux. So delta star is the amount of mass flux in some kind of, how you can say, ওই আমাদের head loss যেরকম হয় in terms of length দিয়ে, সেরকম একটা ইকুইভ্যালেন্স দেখানো হচ্ছে। In a similar manner, another thickness can be conceived which is equivalent to the loss of momentum due to the presence of boundary layer. Okay, so philosophy ta ekhi. So instead of mass loss of mass flux, ekhane amra bar korchi basically we are finding out the momentum flux if there is no boundary layer, and then the actual carried momentum per unit width for due to the presence of boundary layer. So the difference between these two is the loss of momentum. Now, if you have an equivalent thickness delta m, by which, as if you are shifting the boundary to take into account this momentum loss, so which can be written as rho u naught square delta m, and that will be equals to this integral, that is the loss which is evaluated, and then again it is being approximated for the boundary layer thickness 0 to delta instead of 0 to infinity, okay, to get the expression of momentum thickness. So one is delta star, that is the displacement thickness, and the other is momentum thickness. In some books, this delta m is written in terms of theta also. Both are same. Okay. That's just a change in notation. So delta star and delta m, or delta star and theta, are the two very important parameter describing the boundary layer, and that will be basically appearing in the very next topic, which is basically the integration of this governing equation, mainly the momentum equation. So the integral effect, actually, if you want to find out, that means actually the governing equation that we have derived using this order of magnitude analysis is the differential form. So the integral form, if you want to get, you need to integrate this equation, and it is a finite integration of within the limit 0 to delta. That means with the boundary layer thickness you are going to integrate. So, and that leads to a equation which is known as von Karman momentum integral equation, which actually gives us kind of an approximate, it's considered to be an approximate method to solve the boundary layer. That means basically, what is the objective of this studying this boundary layer theory? One very important aspect of boundary layer theory, study of boundary layer theory, or so to say, to find out the relationship delta with respect to x, is ultimately we are going to know, or we are going to evaluate the laws that will take place for the movement of the surface through fluid. So due to the presence of boundary, as we can understand, the flow gets affected. So due to the presence of boundary, the flow gets affected means it is basically because of the shear stress or because of the viscosity. So some kind of loss is being taking place, and that loss ultimately is going to be manifested in terms of loss in the energy, isn't it? Because of this boundary layer and the shear stress that is actually going to oppose the motion of the body. All right. So that is basically the frictional loss, we can say. Okay. So we need to evaluate properly that particular power loss or energy loss, you can say. Once you can able to identify the amount of loss that will be there due to this kind of a surface of the body, so then you can able to find out probably the amount of power required, or that will be required to overcome that particular loss. Okay, so that power will always be required because of the typical shape of the characteristic of the surface you are having. So that power has to be consumed. Okay, now if you want to make a more power efficient car or a more power efficient body which is moving through this fluid, so you need to do something to reduce that the wall shear stress or this friction component. Okay, to have a power efficient vehicle, you can say. So that is our aim actually, because our main objective. So in order to evaluate that wall shear stress and thereby the force required to or the friction component due to the surface, which is also known as skin friction drag. This is a component of drag actually. We will see later. You have if somebody goes through the video in the later part of this course in this particular topic, we'll come across this skin friction drag. So in order to evaluate that, this is the one of the approaches to know the boundary layer thickness, and this von-Karman integral equation gives you a kind of approximate technique to find out this delta as a function of x, or as a function of Reynolds number in Rex. So that is the main, you can say, the objective of deriving this equation. So to find this delta, you need to integrate this x component of momentum equation over the boundary layer. So the range is 0 to delta, and it is dy you need to use. So in the direction y you are integrating, keeping in mind that just outside the boundary layer you are no longer having any kind of gradient del u del y, so that is equals to 0, and your u becomes equals to u naught. Again, this is an approximation. U is not exactly going to be equals to u naught, but it is closely very close to, you can say it is very close to u naught. So these are two, I mean, this is an approximation. So, and of course, just beyond the boundary there, we assume potential flow. That means this will remain applicable. That is P plus half rho U naught square equals to constant, as we have seen in our potential flow theory analysis. Now, if you write it in differential form, you get some kind of a relation of this 1 by rho dp dx minus 1 by rho dp dx, which actually was there. So this actually we will be using. Here you can see this is the 1 by rho dp dx. So actually this is being written in terms of u naught, du naught dx. So your u naught could be a function of x as well. Instead of an uniform flow, if you're having a non-uniform flow, that means u naught is a function of x. So basically you could have the u naught dx present. Okay, so the free stream velocity could itself be a function of x. In that case, actually, your pressure is also going to be a function of x. So dp dx will exist there, and this relation could be applicable inside the boundary layer. So that is the point. Actually, the reason why, I mean, the moment you are having this del p del y equals to 0, or I mean, not exactly equals to 0 if it is being very, very small compared to del p del x, so that it can be neglected. In such case, you can use the relation of potential flow inside the boundary layer as well. Although inside the boundary layer, your effect of viscosity is of prime significance. Okay, you cannot neglect that. Although inviscid flow means there is no viscosity. Okay, so that is you can say another importance of understanding potential flow, because here you can use it inside the boundary layer in some manner. বোঝা গেল? Is it clear?
Yes, sir.
So then basically the remaining part of this integral form, to obtain this integral form, it is mathematics actually, and some kind of mathematical jugglery, you can say, to get the final form. I mean, I think this part, if you go through it, I mean, the video, it is more or less this derivation is being described. And the final form is this one, tau w. So as I was talking about, ultimately we will be interested to find out the Wahl's shear stress. And this is being written in terms of, as you can see, delta star and delta m. I mean, just some 2 steps back, this expression we have obtained can be related with the one momentum thickness and displacement thickness. So this becomes a very compact form of an equation, that is find the expression of Wahl's shear stress with respect to displacement thickness delta star and momentum thickness delta m. Okay, so this is actually applicable for, or on other words, you can say it has been derived for a 2D incompressible laminar boundary layer, but it can as well be used for turbulent flow situation within the boundary layer. Okay, and as it is written, you can see that this forms the basis of many approximate solutions of boundary layer problems. So where why it is approximate, because in the latest part, I mean the next part onwards, you can see here Basically, the main part of the main part you need to know in order to solve this equation is that delta star and delta m. So to find out delta star and delta m as it is being expressed in this form, this is delta m and this one is sorry, this one, the first one, this is actually my delta star. This is delta star and this is delta m. So the knowledge of delta star and delta m will only you have once you know this velocity u, because this is a variable. That means my point is that you need to know the velocity profile u. That velocity profile could be linear, could be quadratic, could be cubic, something like that. So based on that consideration, your delta star and delta m will change, and accordingly your solution of this tau w will alter. So that is why it is an approximate solution for laminar boundary layer on a flat plate. Okay, and you can consider either existence of the pressure gradient that I have said that if your free stream velocity is not uniform, then the first term will be there, will remain, or it will exist, isn't it? And if you consider the flow to be uniform, that means the free stream flow is uniform. It is also denoted as zero pressure gradient condition. So you do not have any kind of dpdx. If you do not have a dpdx, then this particular term will simply be dropped, isn't it? So you are left with only ddx of u naught square delta m. So knowing this delta m will give you some kind of clue for the solution. So in the next part of our analysis, we actually dealt with the cases for zero pressure gradient. That means the first term we have not used, only the second term for different profile. Starting with linear, that is simply this kind of a velocity profile. This is the generic velocity profile, and the linear one appears here as it is basically a naught plus a1 eta. Eta is basically a non-dimensional form of expressing your delta. It is y by delta. Here it is written as y by delta. So eta is having a zero dimension. It is dimensionless. The ratio of y and delta both are length. So for this kind of a velocity profile, you need to assume it first, and then you proceed for the momentum integral equation. And if you consider zero pressure gradients, it will be more handy, so that you get ultimately, you see, you get this expression of tau w by rho as u naught square by 6 d delta dx. And then if you proceed further, you actually get the solution of delta. That is this one, equation 11, delta by x is equal to square root of 12 by rex. And then you can also find out okay. So this actually, now you can see that after getting this delta by x, that means the expression of delta in terms of x. So it is now only a function of x in equation 12, this shear stress, wall shear stress. And then if you integrate over a length L, that is the characteristics length L, you get the shear force. So that is actually what we call as the total friction force from x equals to 0 and x equals to L. That means this region, that is the formation of and growth of boundary layer, what will be the amount of wall shear stress that will be acting where? That will be acting on the plate. Okay, this point onwards is your fully developed. So now, using boundary layer, you can find out the friction force that will be acting on the surface to resist its motion. Okay, so this is the one of the important objective of having the knowledge of boundary layer theory. Okay, and one can observe if this study is continued for quadratic profile as well, and this gives us a more better solution, which is this 5.0 over square root of RDX. Okay, and it is more closer to the exact solution. I mean, there is another technique which, instead of going through this approximate solution, can give you the exact solution, but that is beyond the scope of our course. Okay, that gives a solution which is also known as a Blasius equation. So that Blasius equation gives you the value of this delta as a function of Reynolds number, which is known as exact solution. That is 5 point something over square root of REX. So if you consider the quadratic form, instead of quadratic form, if you consider cubic profile, it comes more close to the exact solution. So this is basically, you can say, the importance of momentum integral equation, which is then being extended to turbulent boundary layer. Okay, but I think that part we will discuss later, or I left it to you to go through the video and just come out with some kind of your feedback, whether you have understood or not. Okay, so after this turbulent boundary layer, it is basically another aspect of boundary layer theory, that is the flow separation, and thereby formation of another kind of drag and the kind of opposing force. So that part, I think we will do it in another day. The second part, we can say, for NEET, where we will try to complete the boundary layer theory discussion on it. Okay. So in the meantime, I think you should also go through the theory. Go through the solution, or try to solve the potential flow problems, and also go through the problems that you want to have. There is a boundary layer theory problem. We will uploading that. Okay, as I can see, it's a very lean attendance now. Not more than 15-16 students are there. Okay, most of you have left. So I should also leave now. So happy puja. Okay.
Thank you, sir.
So we will be updating the things on WhatsApp. Okay, and also in the classroom. So accordingly, you should keep prepared. But for the time being, you enjoy, but you should be very, very careful regarding the situation. Okay, so remain protected, so that we can hope to meet very soon in our conventional classroom mode. Let's hope for that. Okay. So thank you very much. So after
Thank you, sir. Thank you, sir.
Okay.